Okay, so let's talk about the chapter 5, which is trigonometry. And so before we want to talk about Islamic trigonometry, first we want to look at the precursors to that. And that came from classical Greece and India. Okay. Now, the main reason why the Greeks studied trigonometry was for astronomy. They wanted to figure out where something in the sky is going to be in any particular time. So they want to know, when is Mars going to be in Taurus? That kind of question. When is that going to happen next? So we've already seen some examples where some kind of proto-trigonometry has been done. So someone did Thales, and there was this famous instance where he figured out the height of the Great Pyramid by, he figured out the time in which his shadow, when he was outside, when his shadow was the same height as himself. And so at the same time that he did that, he measured the shadow of the Great Pyramid, and he used that to come up with the height of the Great Pyramid. So he's just using similar triangles. So it's a very elementary type of trig. A little bit more sophisticated, we saw Eratosthenes figure out the size of the Earth pretty accurately because he saw that at the summer solstice at a town in Cyrene, if you put a stick in the ground, it would have no shadow because the sun would be directly overhead. But if you were in Alexandria and did the same thing, the stick would cast a shadow which was 1/50th of a circle. Okay, and so by thinking of the sun being basically far enough so that the sun rays are parallel between the two places, basically that then means that the distance between Cyrene and Alexandria must be 1/50th of the circumference of the Earth. And he got a pretty good value from that. So notice no degrees or anything, just working in circle measures. And then there was another famous one, Aristarchus, I think someone talked about, which was trying to figure out the relative sizes of the sun, the earth, and the moon, based upon facts like you look up and you can measure the angle the sun makes or the moon makes. When there's an eclipse, the moon covers the sun. So that means in relative, they've got the same relative size. So that's because the moon is closer. So the sun is as many times bigger as it is further away from the moon. Things like when there's a half moon, and that's going to happen when there's kind of going to be like a right angle triangle between the sun, the moon, and the earth. Measure that angle, and he measured an angle that was short of 1/30th of a quadrant, i.e. so you have a triangle which was 90 degrees, 87 degrees, and therefore 87 degrees between the moon and the sun, and therefore 3 degrees from that, and from that you can figure out sort of the relative sizes of things. Of course, that was way off because the angle measure is so delicate. The actual real angle is something like 10 minutes, not 3 degrees. So it was way off. But anyway, they could do these kind of trig kind of like things. And so this came up all the time in astronomy. And we've already seen that to the Greeks, the way the heavens must have must move is with circles, because that's kind of like the perfect shape, and that's the heavens being perfect must be the by. So this is how Plato reasoned. And so they had this idea of the sphere, the spheres of the heavens. So the earth was at the center, and there were spheres on which the planets, like the sun, the moon, and all the planets were fixed, and they would go round in circles. So Apollonius, who we know before from his conics, came up with a couple of clever ideas, and that was the idea of ecenters and epicycles. Okay, so this is, for example, E is where the Earth is, and here's the sun going around its sphere. So his idea was that the Earth isn't at the center of the sphere where the sun is, that the sphere for the sun is a little bit off center. And the reason, and he came up with this idea because once they started measuring the seasons, they found out that, I don't know if you know this, but each season is not perfectly even. So I'm talking about astronomical seasons. So astronomical seasons go from, summer solstice to autumn equinox to winter. What do you call the winter? Is it a winter solstice? Yeah, to vernal equinox, etc. And so if you look at those lengths of things, they're off by around a couple of days. So, for example, I think spring is longer than summer by 2 days. And so this kind of explains that, right? Because if the sun is going around here, and you can see that in each quadrant, it's spending a different amount of time, and each quadrant refers to a season. So that's that. And so this thing here is called the ecenter, and this circle is called a deferent circle because it's off center. And so you've all heard of eccentricity. That's for, like, we talk about eccentricities to measure how much an ellipse is from a circle, but actually eccentricity is older than that. It refers to how much the circle is deferent. So you look at this ratio between the distance from the Earth to the center, and you compare that to the distance from the Earth to the sun. And that is the eccentricity. And then you've got other words that you might have heard of before. So this P here is the perigee. That's where it's the closest to the Earth. And this is the apogee, where we're furthest away from the Earth. And we still use that thing when we talk about orbits. And the other thing that they noticed was retrograde motion. So if you look at, say, Mars going across the heavens, every now and again it stops and moves backwards. And Apollonius had the idea that, okay, not only is there a deference there, but the planet is actually not on the sphere, but it's on an epicycle. It's in a circle that's on the circle. And so it's going around here at the same time that the center of that is moving along. And if you go ahead and see what that would happen, you would see that every now and again you would get retrograde motion. Okay? And so this really gave a lot of stimulus to be able to, well, let's try and figure out what's actually happening here. So that means you've got lots of parameters, right? And you want to find out these parameters. You want to find out what is these ratios, these eccentricities. how much is it, how long does it take to make a cycle? That kind of stuff. Unfortunately, Apollonius couldn't do it because he didn't have trig. And so the hero of the story is Hipparchus. So he was in the mid-2nd century, right around 150 BC. And he borrowed some stuff from the Babylonians. So he borrowed the idea of degrees. So that there's 360 degrees in a circle. That was a notion that came from the Babylonians, and he used it because with 360 degrees now you've got something that you can measure things with. So it gives a good scale of things. So as I mentioned before, the Babylonians were very good at computation. So if you're good at computation, you want accurate numbers. So that's why they use degrees. The Greeks didn't care so much about computations until now. So now they really wanted to solve this problem. So now they needed a system in which to do it in. So Hipparchus is famous because he did this famous catalogue of stars. So, and stars and planets, where he went out there and he measured the position of various stars and told how bright they was. So you've all heard of the idea of magnitude, maybe? Like a star is 1st magnitude, 2nd magnitude, 3rd magnitude. That actually comes from Hipparchus. So it's actually one of the oldest scientific measurements they do. So if you ever do an astronomy class and you look at the definition of magnitude, it's really complicated log kind of scale because they make it fit how Hipparchus. So Hipparchus by eyeball said, oh, that's a 1st magnitude, that's a 2nd magnitude, that's a 3rd magnitude. And later on, they actually figured out the numbers to make it fit that. So he came up with a star catalogue. So that means he needed a coordinate system to be able to figure out where things were. And there's actually 2 ways you can have a coordinate system. It all depends, right? So you've got a sphere. So if you want to do longitude and latitude, right, you need an equator and a north pole and a south pole. Now the trouble is that there's 2 candidates for the equator. One is the actual equator of the Earth, and the other is the ecliptic, which is the plane in which the sun and the planets are. And why are they not the same? Anyone?
The Earth is at an angle?
Yeah, the Earth is at a tilt. The Earth is tilted at 23.5 degrees. So these 2 things are different. So if you use the ecliptic, you've got longitude and latitude. And that was what was used by the Babylonians. And Ptolemy, who we'll talk about later, also used that. The ecliptic, right, that's where the zodiac is. So what they did was they split the ecliptic into 12 bands, and they assigned a constellation to each band. Although in fact, there's actually 13 constellations on the ecliptic. I forget which one. There's one zodiac sign that they've just thrown away. And of course, constellations aren't neatly packaged, right? So, some constellations, the sun's only in it for like 10 days, and others it's like 50 days, but they just evened it all out. And then the other thing you can do is right ascension and declination, and that's if you use the actual equator as the Earth's equator as the stellar equator. And that's what Hipparchus used. And you see this point V here, where the ecliptic meets the equator, that's the equinox. So it equals. So V is in spring, and over here is autumn, right? And then up here, we have the summer and winter solstices when they're at their most extremes. Okay, so he actually collected data. And since he had this data, he then had to be able to do trig on it. So he actually needed some trig tables. And so he came up with the first trig function, which is known as, we call it chord. And so the chord is, if you have a circle and you have an angle, chord is just the length of the chord that subtends that angle. Okay, so different from us, right? Because for us, trig are ratios. For us, trig is going to be a length. Trig didn't become a ratio until around much later on, probably around 1600. It's a modern invention. And you can see chord as a trig function because, right, if we bisect here, we get a little right angle here, and we see that this chord, so chord divided by 2 is r sine theta alpha divided by 2. So we can solve for chord. So basic chord of an angle is double of half the sine of the angle. Okay, and so what he did was, okay, we have a circle, it's 360 degrees. That's 21,600 minutes, right? 360 times 60. Using an approximation of 3 8/60 plus 30 60 squared, which basically is comes from Archimedes, right? Because Archimedes said that pi was between 3 1/7 and 3 11/70. And so this is basically the average of those two. You can figure out what the radius is. And so the radius is 5718, or 3,008 minutes. That's 3,438 minutes. Okay, and then from that you can start figuring out some chord values. So for example, if this is 60 degrees, then this is going to be an equilateral triangle. So chord of 60 degrees is 3,438. Chord of 90 degrees, right? Then you're going to have a little right angle triangle there. So it's going to be square root of 2 times the radius, right? Because you've got radius, chord of 90 degrees. You've got a 90, 45, 45 triangle there. And so he came up with a little table for every angle from 7.5 degrees to 180 degrees in steps of 7.5 degrees by using these two identities here. So this one here, can anyone recognize what this is in modern terms, in terms of sine and cosine? Most basic trig identity there is. Right, because this is kind of like a cosine. Right, so this is cosine squared plus sine squared. You've got to take into account the thing, right? And that of course follows because here we've got a right triangle here, so this squared plus this squared equals the diameter squared. And then the other thing was he had a half angle formula, which you can kind of recognize what sine squared of alpha on 2 is something like 1 minus cos alpha on 2 or something like that. But anyway, it corresponds to a modern trig identity. So he could figure out the chord of any complement and he could halve it. So if he knew, he started off knowing 60, 90, oh, and 180, of course, because chord of 180 is just the diameter, right? Then you can just go, okay, you can halve, complement, halve, complement, halve, and complement, etc. And if you just go through that all the way, you can get steps of 7.5 degrees, and that's as fine as you can get. Okay. So his actual works are actually lost. We only know about his works. I think his star catalogue, it's famous, but his actual work on trig is lost. But we know it because it really influenced, it kind of split off into two streams. One was Ptolemy, who we'll talk about next, and also Indian astronomers. So how did Hipparchus get to India? Can anyone like to guess? Anna, I think this is in your presentation. Who from Greece got to India?
I didn't do India.
Oh, didn't you do?
I was trying to.
Oh, you did the one before, did you? The history one.
Yeah, I was Greece.
So, oh, you didn't do it to Alexander the Great?
No, I did.
Yeah.
Yeah, oh yeah, Alexander the Great, yeah. Sorry, that was so long ago.
Yes, Alexander the Great got to India, and so that was the cultural link between Greece and India, and so the Indians knew of Hipparchus, but they didn't know about Ptolemy. So Ptolemy refined the system quite a bit. The Indians refined Hipparchus in a different direction, and what we'll see is then those two join together when it comes to the Islamic, when it comes to Baghdad in around 800. Okay. So the big invention of the Indians was sign, because you can kind of see that it's kind of annoying to have chord, right? Because it's double the sign, you know, you're doubling things. So it's all the identities are much simpler if you use sign instead of chord. But anyway, let's look at Ptolemy. So Ptolemy, so when was Ptolemy again? So he was early 2nd century. Right. So his famous book is The Mathematical Arrangement, which is also called the Great Arrangement. So great arrangement, i.e., it's like the universe. It's like how the universe is put together. So that's that. The Islamic mathematicians translated that as al-Majisti, right? And from the Greek for greatest. So you see they're doing a little bit of a pun here. So it's great can mean big, but it also can mean fantastic. So they're saying, so here it was talking about how this is the big arrangement, how everything, and here they're just saying, well, this book is just the greatest. And really, it is probably the most successful science book of all time, because it was the standard text from like 100 to 6, like for 1500 years, it was the premier scientific book. But of course, it then got completely rewritten by Galileo. I used to think that this must have been crap, right? Because it's all based upon the Earth being the center of the solar system. How silly is that? But actually, it worked, right? Because the problem was this. So you've got the sun, the moon, and the 5 known planets. And the question is, where will it be at a given time? And using this book, you could figure that out. And it was not until Galileo and the telescope that measurements became precise enough to show that this was false. So within the pre-telescope world, this gave you the correct answer. So it's not crap. It's actually really, really good. And then this was in the 12th century, that sort of became Almagest, and that's why we call it the Almagest. So So he goes through all the things you need to know to be able to figure out where a planet is. So the first thing, order of business, is to do some trig. So he takes the system of Hipparchus and he refines it. Okay, so he needs a table of chords, and 7.5 degrees is just not going to cut it, right? It's just not precise enough. He wants a table like of every half degree. Okay, so the first thing he did was, instead of 5718, he just made it the radius 60, just to make computations easier. Okay, and so he came up with a table of chords from 0.5 degree to 180 degrees in steps of 0.5 degree. And as well, he gave a system to interpolate between the things. So given any angle, you could figure out the chord of it by using some interpolation. So let's look a little bit at how he constructed his table. So first, so you'll remember when you did trig, you figure out like the trig, the sine of 30 degrees and 60 degrees and 45 degrees, right? Remember, you use that from taking an equilateral triangle or a square. Well, that's what he did. He used Euclid, and he did 36 degrees, because we know a decagon is constructible, so you can actually figure out. So using the same thing, you do 36, 60, 70, 72, that's the pentagon, 90 degrees, and 120 degrees. Right. So you can do that using Euclid, and you can make those values as accurately as you like, because it's just square, they're just square roots of things, which we know how to compute. Okay. So from Hipparchus, he had formulas for complements and finding half angles, but he came up with another formula, two other formulas, which was a subtraction and addition formulas. So you all know, right, there's formulas for like sine of a plus b and sine of minus ab, that sort of thing. And that's Ptolemy's theorem. Given any quadrilateral inscribed in a circle, the products of the diagonals equals the sum of the products of the opposite sides. Okay? And by appropriate choice, then you can interpret these things right as chords. And so you get, right, this is 120, of course, is just the diameter. It's just, like, for example, AC. And so with this, you can get an addition and a subtraction formula. Okay, and so with his difference formula, since he knows chord of 72 and 60, he can figure out chord of 12 degrees using that formula. And so then he halves it, 6, 3, 1.5, and 3/4 degrees. But there's a problem, right? How do you figure out sine of a chord of 1 degree? To get 1/2 degree, right, you're going to have to trisect this. And we know that that's not possible in the Euclidean sense. So he could have made a table of, every 1.5 degrees, or every 3/4 of a degree, or every 3/8 of a degree, but he wanted one of every 1/2 degree. So he's going to have to do some kind of approximation. All these other ones he can do super accurately, right? Because they're just square roots. And we know that you can take a square root that had arithmetic that they could just do it to as many places as possible. So I think it's fairly clear then that probably Ptolemy had computers. By computers, I mean the old sense of the word computer, which was like people whose job all it was to do calculations. So he probably had a team of computers who were doing all these calculations for him. So how did he get 1/2 degree and 1 degree? Well, he used an inequality. So if you've got chords BA and BC, with BA less than BC, then BC on BA is less than the ratio of the arcs. So the ratio of the chords is less than the ratio of the arcs. I think the modern thing is something like sine alpha on sine beta is less than alpha and beta. There's a modern term of this. Okay, so using this inequality, we've got the chord of 1 degree is less than 4/3 of chord of 3/4 of a degree, and that's 1, 2, 50, 40. And chord of 1 degree is greater than 2/3 of chord of 1.5 degree, and that's 1, 2, 50. So we know that chord of 1 degree is between these two things. So he just said to two sexagesimal places, then this must be the chord of 1 degree, and that must be, and we just halve it to get the chord of 1/2 degree. And that's actually correct to around 5 decimal places. Okay, so he's got lots of values that he can find super accurately. And then he's got values in between that he can do to 5 decimal places accuracy. So that's how he constructs his table. Meanwhile, what's happening in India? So there's a book called the Surya Siddhanta. So again, the Indians are also interested in astronomy, as are the Chinese, right? Everyone wants to do this. It's around the 4th or 5th century, and that's the first use of sine. Okay. So I think the Sanskrit word was something like that, which meant bowstring. So it means like chord again. Chord is actually both the Latin and the Greek for that. So they figured out sine, and the reason why they use sine is right, it's just easier to use than chord. So they notice that. But they give it for every 3.75 degrees, right, which corresponds to 7.5 degrees for chords. From 3.75 degrees to 90 degrees, that corresponds to 7.5 degrees and 180 degrees for chord. And they use a reference circle with radius 3, 4, 3, 8. So this is obvious that this comes from Hipparchus, right, because they're using the same radius. All this, right? So in Baghdad, in around 800, they had translated the Almagest. They translated the Sanskrit book all at the same time, and it's from this that we get our modern trig when these two kind of things combine. So interesting, where does the word sine come from? So the Arabic scholars, when they translated, so when you translate something, you come to a difficult word, you've got like two options, right? You can translate it into a word kind of like from your language, or you can take that word and you can just sort of make it a new word, like you can just turn that to an Arabic word by just writing it down. Okay? And that's what they did. And then in the 12th century, when these things were translated into Latin, the Latin translators had a similar problem. They had this word, and they didn't say, what is this word? And instead of it realizing it was a Sanskrit word, they thought it was an Arabic word. And the closest Arabic word was something like that, which means cavity. What's the Latin word for cavity? You've all got it in you, behind your nose. sinus. So sine comes from sinus. So it's just a mistranslation. So this is supposed to mean like bowstring, supposed to mean chord, but it got translated as cavity. I always find it a funny little story. Okay, and so that's today. Yep, and we'll continue looking. Next week, we'll start looking at Islamic trigonometry. Whew. What's the time, by the way?
Huh?
The time?
Oh, it is 11:12.
11 to, okay. So I did around the right amount of time.